Hello all, good afternoon, good morning, good evening. Welcome to my course on methods of adhesion measurement theory and practice. So, today we will go to the next lecture, the second lecture of this course. So, before that I will like to talk about the summary of the last lecture. So, in the last lecture we talked about this deformation field in this at a point x, y, z inside a body which is undergone some deformation under some stresses, and we defined the normal strain, that is E x x is equal to del u by del x, E y y is equal to del v by del y, so on. And then we have these shear strain components which were E x y is equal to half of del u by del y plus del v by del x. Like that we have epsilon E x z, E y z, and like that. Then we define the strain tensor which is E x x, E x y, E x z, E y x, E y y, E y z, and E z x, E z y, E z z. So, here this is a symmetric matrix, that also we said. So, what it means is that E x y is equal to E y x, and then we also defined this E x x plus E y y plus E z z, which is actually the trace of this matrix, and here this summation of that is called the volume strain. And we also know that the trace of a matrix is invariant with respect to the coordinate transformation. And since it is a volume strain, so therefore E x x plus E y y plus E z z, this is equal to 0 for an incompressible material. We also showed that this matrix, the strain tensor, so that can be transformed to obtain the principal strains or principal directions 1, 2, 3, these are the eigen values and eigen directions, and we can define this E 1, E 2 and E 3, and these are the principal strains. And we also discussed about how to express these strains in a with respect to a different axis. For example, the strains are defined, let us say, with respect to x, y and z axis, and let us say now that we want to define in terms of this x dash, y dash and the z dash axis, and this x dash has a direction cosine of L1 with respect to x. So, L1 is actually is equal to direction cosine, so cos of, let us say, represented as this is x dash comma x. So, here x dash, and like that M1 will be defined as cos of, let us say, y and x dash, like that. So, these are the direction cosines, and with this direction cosines one can actually express these strain components E x dash with respect to this E x x, E y y, E z z and all that with respect to this equation. And we can also express these shear strains, that is E y dash z dash with respect to this strain components E x x, E y y, E z z, E z x z y and E y z by this kind of expression. So, all this we covered in the last lecture. So, today we will like to talk about what is known as the stress analysis. So, what exactly we want to do is the following. So, we have this body which is undergoing, let us say, some deformation, and inside that body there is a point O. So, what we want to find out is that what are the stresses at this particular body. By what I mean by that is that this particular point O is there, and this O is on this particular surface S, and on this surface around O there is an infinitesimal element which is called the ds. Now, this so we want to find out that what are the stresses at this particular point. So, let us say this particular element ds has a normal which is represented by nu vector, and so this particular elemental area is defined by this nu vector, and the force that acts on it per unit area, that is this F nu. F nu represents that the F, there is the force vector that acts along that acts on this particular surface which is perpendicular to this nu vector. That is what meant by this F nu vector. So, now what we can say is that this F vector or the F force that has projections along 3 axes. okay, which is x, y, z axis. So, these projections along this x, y, z, okay, that can be represented with respect to this is let us say f nu vector. So, this can be represented as x nu, y nu and z nu. Let us say this is y nu and this is x selection, this is y nu and this is z nu like this. So, this is the force. So, x nu is the force that acts along the x axis per unit area, the surface of area of a plane that is normal to the nu direction. So, this nu represents that the surface is perpendicular to the nu axis and the x represent capital X represents this is the force that acts, okay, along x axis per unit area of this particular area which is perpendicular to the nu. So, this f is represented as x nu cos cos x nu. So, this is the direction cosine, then y nu is the cos y nu and the z nu into cos z nu. So, the element ds is subject to therefore the force x nu into ds. So, ds is the area, y nu is and z nu y nu ds into z nu ds. So, this is that for this small element and so therefore, if I have the if I find out the summation, okay, of over the whole area, okay, over the whole area. So, here ds is only small area. So, we can get this. So, this is the area integration over the whole area. So, this is x nu ds, y nu ds and the z nu ds. So, these are the forces that acts, okay, and on this element, on this elemental area ds. So, these are the surface forces. However, around this point there is also a volume element and so let us say this is the point, around this is a volume element and this volume element dx, dy and the dz. So, this is the volume. So, multiplied by rho, this becomes the mass and so there is a force that acts the per unit mass of this particular body and that is called the body force and so that can be represented as multiplied by dx d nu dz rho into rho into capital X, let us say. So, this is the force per unit volume that acts on a volume element. So, the forces that act on this particular point has got these surface forces and also the body forces. So, the force that on each particular body can be divided along these three coordinates x, y, z. So, these are the body force per unit mass of the material. So, the total body force that acts on this particular whole body, okay, along these three axes can be represented as rho capital X into dx dy dz. So, here this capital X means this is the body force that acts per unit mass of this particular body. So, this is the body force that acts on per unit mass of this particular body. So, rho into x into dx dy dz and rho into y into dx dy dz like that. So, we can actually sum it up this surface force and the body force and we can see the balance and the balance will result in some kind of acceleration. So, this fx, fy, fg which are here are the components of acceleration at point x, y, z at a time t along the three coordinates. So, we can have this basically balance of forces and that will lead to this rho fx. So, this is the balance of forces along the x direction. So, x nu ds, this is the integration over the area. So, this is area integration, okay, and this is the volume integration, this is the volume integration. So, this is again the volume integration. So, like that. So, this particular equation that defines the balance of forces along the x axis, along the x axis. Similarly, this is the balance of forces along the y axis and this is along the z axis. So, similar to this force balance, we will also have the torque balance and that can also be written. So, for example, that suppose that you have this let us say this is the y and z axis, let us say this is y and this is the z axis and this is the x axis is perpendicular to this particular point, the particular this plane, okay. And let us say that this is this particular point x and y, x, y, z and so this particular point is at a distance z from the y axis and at a distance y from the z axis. So, the force that acts along the y axis. So, that is actually let us say this y nu, right, y nu, and let us say the force that acts along z axis and let us say z nu. So, we want to find out that what is the torque of these forces about the x axis. So, we have to multiply, you see here that the z nu into y. So, z nu into y, okay, minus z into y nu. So, that will be the torque. So, z into y nu. So, this is the torque is the anti-clockwise direction. So, anti-clockwise direction is positive. So, this is positive here, minus z into y nu. So, z into y nu is the opposite directions, the clockwise direction. So, that is negative here. So, this is the torque that of the forces. This is actually not body force, this is surface force, surface traction. It should be right, should write it as surface, not body. So, body force is this. So, this is a surface force. So, y into z nu minus z into y nu, and this is again integrated over the area. So, similar to this surface force, you have the also body force. So, body force will be rho into y z minus z y into dx dy dz. So, here this y z is the torque, okay, of this z component of the body force about this x axis, and this is the z y, okay, this is the torque, okay, or moment of this particular force about the x axis. So, we have the total torque, okay, that is represented by this right hand side because of the surface and body forces, and the unbalanced torque, okay, will lead to this particular unbalanced quantity in the left hand side. So, that is the way the force balance or the torque balance that needs to be done. So, the x, y, z, so this is x nu, y nu and z nu, okay. So, these are the forces that was there in this particular body. So, this was this ds, that was the small area, and this was the nu is the vector that is perpendicular to the ds area. Now, on this particular surface, this is the, let us say this is the x direction and this is the y direction and this is the z direction. So, that was the case. Okay. Now, we want to represent this x nu, y nu and z nu, okay, with respect to our own coordinate system. So, that is x, y, z. So, basically what it mean by that let us say this is x and this is y and this is z, okay. And so, we can think of a a tetrahedron. So, where it is something like this, tetrahedron. So, this tetrahedron has got this particular area. Let us say that this is A, B, C and O. So, let us say this is O point and let us say this is A and this is B and this is C. A, B, C, okay, now let me do it differently. This is, so this is just to keep it consistent. So, let us say this is A here and I have written here this is B and this is C. So, let us say this is B and this is C, and so now the area of this ABC, okay, is given by the delta is the area of, let us say, triangle AB plane ABC. So, like that we have got this plane AOC, that is the area that is AOC, and then we have got this area BOC and AOB and like that, and this area of this AOC that can be represented as delta into cos of, this is AOC is perpendicular to the y axis. So, it will be y and mu, y nu, okay. So, ABC is perpendicular, this particular plane ABC is perpendicular to the nu axis, okay. So, therefore, its area is delta, if its area is delta. So, the area of triangle AOC, that will be this delta into cos of y nu, because that is the direction cosine of this particular plane AOC. Like that, the BOC will be delta cos of BOC is perpendicular to the z axis. So, this is will be z nu, like that, and like that this is AOB will be delta cos of x nu, okay, like that. And we can now find out the balance of the forces about the x axis. So, the forces that acts on the force axis will be something like this, these have already described, and will be something. So, forces that act on the plane ABC, that means ABC, that is x nu into delta, y nu delta and the z nu delta. So, these are the x, y and z direction respectively, and the force that will act, okay, on AOC, okay, that will be xx, and this is delta, and this is AOC. So, it is cos of x nu, and this is y nu. So, this is yx, y, it is x, and there is a, it is x along the opposite direction. So, delta, it is cos of, this is y nu, and like that z nu. For this component also we can write, the z direction also we can write, and so this is actually should be minus, because it acts along the x opposite to the x direction. So, so here like this. So, therefore, we can actually like that, for we will have for the BOC surface, and also we will have for the AOB surface for all these cases. Okay, we will have the x component force, and then y component force, and the z component force, okay, as I have written here. So, here so now here you can see that around this circle. So, these forces are all acts along the x axis, these forces all act along the x axis, okay. Like that, these forces acts along the y axis, like that. And so, therefore, we combine all these forces, and then since this tetrahedron has to be in that equilibrium, so we can write it like this, that the forces are all equal, and the total force should be 0. So, therefore, we will come out to be x nu is equal to xx plus cos x nu plus xy cos y nu, and xz cos z nu, like that. And therefore, we will also have the y nu is equal to yx cos x nu plus yy cos y nu plus yz cos z nu, and z nu is equal to zx plus into cos x nu, zy cos y nu, and the zz cos z nu. It is like that. So, these are the way that this x nu, y nu, and the z nu, that can be expressed, and that can be substituted, okay, in the force balance equation that is over here. So, we can actually substitute this expression over here, and so we substitute over here this force balance, and so therefore, we will have here this is this rho f x dx dy dz, that is equal to, so it is rho, it will be capital X dx dy dz, and the plus this is area integrations, or area integration for the area, and instead of x nu I will write xx cos of x nu plus x y cos of y nu plus x z cos of z nu, and this integration is being done over the surface, over this particular surface. So, like that. So, like that we can write, okay, the force balance for all the other directions, and or what you can notice here, that this is a volume integral. So, this is a volume integral, and here it is a surface integral. So, in order to have the consistency, we will like to have the volume integral, okay, in all the terms, and so therefore, what we will do is that we can use what is known as the divergence theorem, and in divergence theorem, okay, this xx cos nu plus kxy cos nu and xz cos nu dx. So, this term and this integration actually can be converted to the volume integral, and that can be written as this particular equation. So, so instead of this we can actually write this. So, this is del xx by del x. So, this is the partial derivative of this stress xx with respect to x, this is with respect to y, with respect to z, and like that. And these are the see that these are the surface forces which acts along the x axis, and then of course, here is the body force term, and this is the acceleration term that is there. So, now we can combine, okay, all these terms which are all now is basically volume integral, and so therefore, we can get after combining all that this particular equation. So, see here all the term are the volume integral, and so these are all included here, and the right hand side therefore is equal to 0. So, the whole integration of this whole thing is equal to 0, and so therefore, at every point, okay, this integrand that has to be equal to 0, and so therefore, what we get is this particular equation. So, here it is the derivative of xx with respect to x here, derivative of y x with respect to xy with respect to y, and xz with respect to z, and like that. And so, this is known as the stress equilibrium relation, and we can write this for all the terms. Over here this rho fx, we can write it as the acceleration term. So, we can actually write it as rho del square u by del t square. So, u remember is the deformation or displacement along the x direction, v is that for the y direction, and w is that for the z direction. So, here we can actually have this as the stress equilibrium relation along the for the x direction, this is the y direction, and this is the z direction. Now, in whatever we, in most of the cases problems that we will solve, we will have this body at equilibrium. So, we will not consider this acceleration. So, the acceleration term is equal to 0. So, the right hand side is actually 0, and so therefore, we have this equation. And if we say that we do not have any body force, then we have got this equation. So, this equation where the body force terms are also equal to 0. So, x y is equal to z is equal to 0, that is what we have. So, similar to that, we can also do the torque balance. So, in the torque balance also we can substitute the surface integral, we can replace it by the volume integral, and we can find this particular expression. So, after substitute for the surface integral to volume integral, okay, we can do this, we can do a little bit of algebra derivation, and we can find this expression. And here again, as you can see that this point term has to be equal to 0 at every point x, y, z. So, this is actually equal to 0. So, we can actually find out the derivative of this point. So, now it is it will be, say let us say it is del by del z, and this is y here, and this is z z, let us say, minus this is let us say y z, and plus this is let us say z y, plus it is let us say y, and this is del z y by del y. Okay, so here, no, I think I messed up. Sorry, I messed up here. I will do it once again. So, here this is y, it is del z by del z. So, here it is minus z and minus yz, it is yz and minus it will be z and del of yz by del of z. So, that is from this term, and then plus it is del, it will be z of y minus y into del z y by del y minus this is z, it will be del y by del y, and then plus the next term. So, this will be equal to 0 because we can find out derivative, we have just find out derivative, and we can combine all these terms together. So, after doing all that, we will have something like this, we will have y into this minus z into this plus z y minus y z. So, this is after all this derivation this derivative that we find, and we combine all these terms, and we will get something like this. So, here we can see that this y into this term. So, this actually comes from the stress equilibrium relation, and that will be equal to 0 here. Again this term also comes from stress equilibrium relation, that will also be equal to 0, and this term therefore also has to be equal to 0. So, this z y comes out to be equal to y of y substitute z y subscript z. So, what it means is that z y, this is the shear stress that acts along the z axis on the plane that is perpendicular to the y axis is equal to the shear stress that acts along y axis on the plane that is perpendicular to the z axis. So, z y is equal to y of z. What it means is that this particular matrix in which we have these 9 stress components, okay, here these are actually equal, these are actually equal, and similarly these are also equal, x z is equal to z x, that is also equal. So, we have got this in essence we have got actually 6 independent stress components, and the stress tensor, that is actually symmetric. So, we have deduced this, to summarize, we have deduced this stress equilibrium relations, and these are the stress tensor components, that means the stress components, and this is a symmetric, and so therefore, this z y is equal to y z, by x z is equal to z x, and y x is equal to x y, that also we have derived. So, we can actually generalize this idea that y z is equal to z y. So, here projection of stress acting on the first plane. Okay. So, this the stress that is on the first plane, that is actually let us say on plane z. So, that is y, is projection on the acting on the normal to the second plane. So, that is actually the y here the y direction. So, this y z is actually projection of stress acting on the z plane, okay, on the normal to the second plane, that is y plane, okay, y direction, that is equal to the projection of the stress over here. So, z y is equal to y z. So, this term, this particular statement, okay, we can actually generalize for any two normal normal directions, nu dash and nu double dash. The normal to plane 1, that is let us say nu dash, and normal to plane 2, that is actually nu double dash, and we can do this transformation of the stresses from one coordinate to the another coordinate, or one plane to another plane, we can do that. And so, you know, having going by that idea, we can actually do this coordinate transformation, okay, here too. So, for example, here this x, y, z are the coordinates that we already have, and let us say x dash, y dash and the z dash, these are again 3 orthogonal directions, okay, which has the direction cosines L1, M1, N1 with respect to x, y, z, L2, M2, N2, y dash with respect to x, y, z, and z dash L3, M3 and N3. So, these are the direction cosines of z dash axis with respect to x, y and z. So, we have this coordinate system x, y, z, and in which the stresses are defined, let us say, okay, and now let us say we have got the new coordinates, that is x dash, y dash and the z dash, and in which it has got this direction cosines, okay, and we can therefore write down this particular equation. We can do this derivation, and finally, we can get this equation x dash and x dash y dash, like that. So, we can derive the other components also, like y dash and z dash and x dash z dash, like that. All the other different other components that we can derive, okay, by using this general equations, and we can actually show that we can actually add this x dash plus y dash and the z dash dash dash. So, if we do that and we use this expression over here, we will get something like this, L1 square plus L2 square plus L3 square into x and like that, and 2 L2 L1 M1 L2 M2 plus L3 M3 xy, like that. And here we can use these results, which are is equal to L1 square plus L2 square plus L3 square is equal to 1, okay, like that. And we do that, we find that x dash plus y dash plus z dash is comes out to be xx plus yy plus zz. So, what it means is that in this particular matrix, so xx plus yy plus zz, this actually is the summation of this diagonal terms, and so the diagonal terms that remains independent of the directions. So, xx plus yi plus zz, that particular term, okay, it remains independent of any transformation of coordinates, okay, that is what it comes out. And we can also find out the eigen directions and eigen values, okay, by using putting this determinant of this matrix is equal to 0, and that way we can obtain the normal components or the principal stresses, and in which we have only the normal stresses and no shear component. So, we can do that, we can find out the principal stresses and the principal directions. So, there is a small example problem that I think I will take in the next class or next lecture. Thank you.